We have with us three very interesting speakers today that I'd like to introduce. Starting with myself, I'm currently with the managing principal of Jacobs, which is a very large firm in the United States, and I'm the managing principal of architecture and design. For me, that's a very interesting opportunity to take a long history of my career in high-rise buildings and see if I can't get my arms around a larger firm to apply it to exactly the same issues we're all focusing on here in Mumbai. The next presentation will be entitled the Ctbuh Guidelines for Wind Tunnel Testing of Tall Buildings, and will be given by Peter Irwin and Graeme Wood of RWDI.
Okay, be good to get the first slide up if we could. Okay, thank you. The origin of this talk came out of some discussions that took place in New York last fall when there were two wind tunnel testing labs trying to compare results on the same building along with the structural engineer. And out of those discussions, we decided that it would make life easier for both the structural engineer and for those doing wind tunnel testing if we could have a guideline that would explain to the designers, architects and engineers, in simple terms what wind tunnel testing is about, and also that would have certain common formats that wind tunnel testing results could be presented in. It would make life a lot simpler. So that was the origin of this initiative to create a guideline for wind tunnel testing of tall buildings. The idea is that we would produce a first draft of this guideline by a fairly small group. In fact, just those three of us, RWDI, CPP, and Arup. And then, having produced that draft, we would then invite a well-qualified committee to review it. We will then incorporate their comments into it, send it out one more time, and then by the end of this year we would have produced this guideline. Now one thing that this slide is meant to illustrate is just the importance of wind loads as the building height increases. It looks like a kind of exponential increase, and it is in fact a real fact that the wind loads on a building are very sensitive to wind speed. They can depend in the classic sense on wind speed squared, but once you start looking at a crosswind response of buildings, it can depend on wind speed to the power 3 or even to the power 4. So the wind loads have a big impact on the cost of the main structure, the cost of the cladding, the building motions, and sometimes on very tall buildings they can even affect the very feasibility if the wind loads prove to be so high that the project becomes no longer feasible. So wind tunnel testing has become well established for these, especially for really tall buildings. And this is a typical setup, and this in fact is the project where the three of us were sitting down trying to resolve differences last fall. It's in Qatar, and the black building in the middle was the model building being tested. Now, why do we need a guideline? Well, wind tunnel tests are frequently done on tall buildings, so it isn't just an academic thing, and can have a big impact on the cost. There are standards and manuals that do exist, but they've mainly been written for wind engineering specialists and are pretty incomprehensible, I think, to the average designer because they are so specialist. There is, for example, the ASCE Manual of Practice, which I helped write, and there's also even an ASCE draft standard for wind tunnel testing that has not yet been published. But I think there's a need for the non-specialist to have a booklet which would help them understand what wind tunnel testing is about, and would avoid getting them having to read very, very detailed technical text, which they probably don't have time to go through. So the Council on Tall Buildings is aiming to fill this gap by having this guideline that'll help specialists and also the non-specialists. The objectives would be education of non-specialists about wind tunnel testing and the associated analysis. It would be promotion of good practice at the wind tunnel laboratories. It would make comparisons between the different sets of results easier. And also it would be easier to identify the sources of any differences. And finally, the clarity of the assumptions made by each wind consultant would be more easily laid out and identified. And this is important because there are assumptions, as we'll see later, particularly when it comes to combining wind tunnel data with meteorological statistics. Meteorological statistics, they remind me a little bit of Disraeli's phrase, there are lies, damn lies, and statistics. And wind data can be difficult to interpret, especially in locations where the sources of the data are not very good. This is the same project in CPP's wind tunnel, and when we found there were differences, we obviously were curious to find out why. Well, coming back to the guideline, our plan is to have the initial draft prepared just by the current authors by the end of March this year. Then we'll invite a review committee to provide suggestions by contacting either Ctbuh or one of the authors. And we will also reach out to people who we know are well qualified to do this. The committee's comments will be incorporated in, and then we'll have a revised draft, and then finally we'll produce the final version by the end of October of this year. That's our schedule. Now, the key steps in the wind tunnel method can be boiled down to 5. There's the wind statistics I've already mentioned, which have to be combined with the wind tunnel data. Then there's the construction of the model and the actual arrangement of the test setup, such as simulating the right profiles of wind approaching the model. Then we need to obtain the wind tunnel test data by doing the tests. Again, there's the right conditions have to be made to do that. Then, if we're looking at the building structural loads, we need to incorporate the dynamic properties of the building, which come from the structural engineer. And then finally, that allows us to predict the load effects, such as base moments, floor-by-floor loads, torsional moments, accelerations, deflections, versus return period, which is really what the final aim of this test program is. Just looking at the wind climate statistics, I've given you an example here of a site in Saudi Arabia where the data have been analyzed by different methods. And what you've got here is a plot of wind speed versus return period, and you can see that there is a spread of the results depending on what analysis method you use, what fitting method. Likewise, when it comes to wind roses, these are 2 stations in the UAE quite close to each other, where you might expect them to be quite similar. But they're different anemometers on different sites, and they are not identical. So this requires interpretation by the wind consultant. And then finally, in the test itself, you have to make sure, obviously, that the model is accurate. If you're comparing results, the first thing to do is to check that you both built models of the same building. It's not from the same set of drawings. That you model the surroundings the same way, the wind profiles and turbulence are being correctly modeled, the wind directions that you've tested are similar, the instrumentation's got the right response, that you're even using the same test method, whether you're using pressures or force balances, for example. Is the model so big that it tends to block off some of the air and the airflow in the wind tunnel? These are all different issues which can be gone through, and without going into the details, the guideline will lay these out. and in fact enable the designer to ask questions about this to each wind tunnel laboratory and find out for themselves how these have been handled. The guideline will also have a bit of a primer on the basic actions of wind on a building. Wind, first of all, is highly turbulent, and it's sheared as well. The wind speed increases with height, so that has to be modeled, and that turbulent, sheared wind buffets the building. As you can imagine, the building now being impacted by the airflow approaching it, but it also generates its own turbulence. Illustrated here. I guess we probably don't need the sound effects. This is illustrating vortex shedding off a circular cylinder, but the same happens on a tall, slender building where you get alternating vortices shed off each side, and this causes very large forces in the crosswind direction for some buildings. Some buildings, such as Burj Khalifa, the shape was specifically molded, if you like, to try and eliminate this kind of vortex shedding by constantly changing the cross-section as you go up the height. But many buildings, it's not possible to do that. And the end result is that you obtain a plot like this of, say, the crosswind response versus wind speed. And you can see the response shown by the solid curve rises up to a peak and then drops down again. That peak is caused by the vortex shedding. And if your design speed is, say, where that red vertical line is, well, then you're going to get much higher loads than what you would expect if you had no vortex shedding, up to a factor of 2 or even 3 sometimes. So it's clearly important for the structural designer and for other people to be aware of this very significant phenomenon that affects tall buildings. And I think at this point I'm going to hand over to my co-author, who is Graeme Wood. Graeme is from CPP, and Roy Denoon, also from CPP, is involved in this, as will be others from RWDI.
Peter's mainly talked about the wind climate and how that can be analysed between the different labs quite differently. Now we're moving on to the measurements taken in the wind tunnel and how they could be compared with use of the guide. And this is just a graph of moments, and they've been normalised in the model to make them non-dimensional. And so these would be very easily to compare between two different sets of data quite easily. This is another set of response that again could be easily determined. It's a normalized graph of power spectrum, which is the energy, the vibrational energy in the model. And there's two graphs shown here. One's the along wind, which is the buffeting of the wind as it pushes against the building, and the other one is the crosswind excitation. And the video that you just saw is highlighting that crosswind excitation, and you can see from these graphs that there's a much larger response, so there's a peak in the spectrum. The other thing that's crucial about this graph is that you can see the extent of the frequencies that have been modeled with the base balance technique particularly. You can see that it goes up to about, or the range goes from 0.01 up to 1 hertz at model scale. So you can check that that range is appropriate for the building and it hasn't been truncated because the model's actually vibrating in the wind tunnel, which is really bad. And the other thing that's important from this one is that the spikiness of the spectrum. And when I show you the next slide and we see the dynamic response that would come from the structure, that spikiness in the spectrum becomes very important, or can become very important. So how you smooth the energy in the wind tunnel is very important. And this is a graph of the response of the spectrum of the building. So the previous ones have just been looked at the measurements you take in the wind tunnel, and now we're applying the dynamic information that comes from the structural engineer. And that's the big spike in the spectrum. That's the resonant frequency that's going to set the building off. Now that resonant spike is dependent on the analysis from the structural engineer. And in a peer review process, those structural dynamic informations may also have changed with structural changes in the system. And so that's another key element that we can look at. This also shows you that in the response of the building, there are two dynamic factors. There's the background response and there's a resonant response. And the background response is just the turbulence in the wind pushing the building and getting it excited. And the other one is the excitation of the building at its natural frequency, similar to pushing somebody on a swing. And again, these are very important to compare between the labs. And then, if you combine all that together, the mean distribution and then the dynamic components of the background and the resonant, then you get a plot of response coefficient against wind direction. And again, these can be easily compared between different labs. And the mean in this one would be exactly the same as the mean in the previous one. It's now that this one incorporates the dynamic information from the structural engineer. And you can change the dynamic factors such as the damping, the natural frequency, to show the sensitivity of this response to wind excitation. So that's the structural loads. The other commonly conducted test on tall buildings is the cladding pressure, or really just a pressure analysis. And there's a couple of images of a model there. It's basically a big pile of tubes of spaghetti shoved inside a model of a building. And in this case, between different analyses, you'll be looking at where the pressures were measured on the model. Because depending on how the flow goes around the model, you're going to get a pressure distribution along the surface. So if you've decided to make the holes at different intervals, then you will get a different response out of the building. From these tests, you can also integrate the pressures to get structural loading. You can also look at it for natural ventilation from the pressures across the building, mechanical influences, and so on. And this is a graph of, again, pressure coefficient. Everything's been non-dimensionalized here. And that's really what the guide's trying to push towards, so that these events are fairly comparable between the different laboratories. And you can see in here that there's a pressure tap on the building in a corner, and then you get these distributions. You get the mean, and then you get the peak, the maximum and the minima. And the minima is really happening when the wind accelerates around the corner and causes some significant effect. And this is where the location of the pressure tap on the building becomes fairly crucial to what the magnitude of that pressure would be. So we've now got the wind data on one half, and we've got the data from the wind tunnel in the other hand. And the thing now is to combine both of these together. From an analysis point of view, we can now say if the wind climate is different between the two labs, or the wind tunnel test different between the two labs. And that's a distinction that is been very difficult to make in the past, and I'll go on to show you some of what's been traditional responses that we've got. And you can see in this graph that the graph on the left is showing you the wind climate, and the prevalence of the wind. In this case, it's coming from the northwest or the southeast. Those are your key wind directions. But the graph on the right is showing you that the building is actually responding more strongly to winds from the northeast and the southwest. And it's the integration of these two data sets that gives you the structural design, or the design for the building. And this is another graph along the same line. The graph at the top is showing you the probability of the wind from all directions. And you can see where it's high, that's going to be a high probability of the wind occurring from that direction, and the troughs are going to be where it doesn't respond. This is actually for the Burj Khalifa. And on the bottom graph is the response of the structure. So you can see where it pops up, that's where you would get a high response. And as Peter mentioned earlier, the building was actually twisted to align the two peaks from the structure with the two troughs from the wind analysis, the wind climate analysis, which caused a huge reduction in the loads on the building. But how to combine these loads? There's lots of different ways to combine the probabilities between the wind and the wind tunnel. And these just a list of them here, and the guide will go into a bit more detail, or will go into more detail, because I'm not really going to go into the technical aspects of what all these techniques are talking about. But this is also the fundamentals as to what happens if the two independent sets are similar between the two labs, but when you combine them, you get a big difference. And so it's normally going to be in the way that the data has been analysed and combined. This is a graph a response graph, acceleration in this case. It could be moments, shears, any other wind-induced force on the building. And this is just showing you what would typically be given to the client at the end of a wind tunnel test, which is the final response, the combination of all the data. And comparing two graphs from different labs at this stand, it's impossible to unravel where the differences could have come from. And you can see in this graph that it's got different dampens. You could do one with different frequencies, just to show how sensitive the structure would be to these changes in the properties. So just to highlight, the main differences that normally come out from peer review processes tend to come from wind statistics. The way that the wind data has actually been analysed has a mixed wind climate been taken into account, so you've separated different storm events and things like that. And then, as I've talked about, integrating the wind statistics with the wind tunnel data. And as Peter said earlier, crosswind response, if you have a structure that's susceptible to crosswind response, it can vary as v cubed or v to the power of 4 as a response, which is significantly different than a v squared response. So even if you've got a small change in wind speed, it could result in a large change in total response in the output of the structure. So hopefully the guideline from the council is going to help both designers and wind consultants on tall buildings. Certainly the developer the client who's going to request the job can actually ask questions to the wind tunnel. Have you done these things? How have you modelled the building? And so on. It'll promote standardization, but it won't get away from the uniqueness of wind engineering in the prediction of the response of tall structures. And just as a final comment, if anybody is interested in being on the review committee, could they either speak to Peter or myself, or pass the details to us or to the council? I'll give Anthony Wood's name out there as well, so you could pass your details to him.